All right, section 3.9, differentials. And let's start with some thinking. All right, the first little section here is tangent line approximations. It says, to begin, consider a function f that is differentiable at c. The equation for the tangent line at the point C, f of c is given by. Now, this is simply the point slope form that you learned forever ago. All right? If that's our point, then c is x1 and f of c is y1. The slope of the tangent line is the derivative. So that's y minus y1 equals m times x minus x1. Then you add f of c to both sides so that you have it solved for y. All right, so that's where that comes from. And that's called a tangent line approximation or a linear approximation of the function f at the x-coordinate c. Okay? Now, how would we use something like that? Let's think about it. You've got a function. It's got a tangent line. Aren't the values on the line close to the values of the function when you're close to the point of tangency? Now, a lot of ambiguous terms there, right? Close, close, close. I guess that's one term, but used several times. I mean, let's face it. The value at this x-coordinate between the line and the function, they're not real close together. But for an x-coordinate right here, pretty close. As you get closer to the point of tangency, real close. So what's the advantage to this? Which would you rather evaluate, a line or some really complicated function? A line. Okay? So if we can find the equation of the tangent line, we can use it to approximate values of the function. Now, only near the point of tangency, but it works, and it's easy, relatively speaking. Okay? It's easier than taking some really, really complicated function and trying to figure out what its value is at a certain x-coordinate. All right? So look at the example they have here. It says find the tangent line approximation of that at that point. All right? Take the derivative and then fill it into our equation. That's y minus, and then y1 is whatever f of 0 is, because 0 is our c, equals m, the derivative at 0, times x minus x1. All right, since the derivative of f of x is the cosine of x, then it turns into this. So y minus f of 0, your original f of 0, put the 0 in the wrong spot, didn't I? F of 0, so you take the sine of 0, it's 0, 1 minus 0 is 1, so there's y minus y1 equals m. All right, this takes a little work. You found the derivative here. Now you got to find what the derivative equals at 0, which is 1. So that's m, and then x minus x1, your x-coordinate. All right, and then we get our tangent line. Now, it would take us a little more work and thought than that. I'm trying to go quickly. Okay, so we get the tangent line. We've gotten tangent lines. All right, we did a bunch of those back in chapter 2. If you're given a function and a point, you should be able to get the equation of the tangent line. Okay? Because you find the derivative, that's the slope of the tangent line, and then you use the point to then use your y minus y1 equals m times x minus x1. We did a bunch of those. All right, so it looks harder there when I try to go fast than it actually was in reality. Once you get that tangent line at that point, then look how close you are here. All right, the point of tangency is there. So the value of the function here and the value of the tangent line here are equal. But look how close they are otherwise. They're really, really close here. They're fairly close here, and at this point we're getting far enough away that's probably not a good enough approximation. Okay? With me? Which leads us to something called differentials. The reason it leads us to this is because differentials are also an approximation. All right? Approximations are fine. I don't like it in elementary school when they give them a problem that you can do with arithmetic and they say approximate it or estimate it, because you can just do the problem with arithmetic. And now with the fancy calculators, sometimes a lot of these problems that we're going to find approximations for, we could do as well. But think back, like I've told you before, sometimes calculus is sort of a history of math class. And you got to realize that until very, very, very recently, when everybody has a computer in their calculator, these things had to be done by hand. All right? And when they had to be done by hand, you definitely wanted to use linear things instead of weird function things. Okay? Saves you a lot of time. So, that's what's going on here. So let's read along here. When the tangent line to the graph of f at the point C is, all right, so this is what we came up with a while ago, is used as an approximation of the graph of f, the quantity x minus c is called the change in x and is denoted by delta x. Okay? The change in x is x minus some little bit. That's the change in x. In other words, if x starts as 2 and it becomes 2.1, the change in x is 0.1. Or if it starts as 2.1 and becomes 2, the change in x is 0.1. We rarely care about the direction of the change, positive or negative. Okay? Now, when delta x is small, the change in y, denoted by delta y, can be approximated as shown. So, that is a definition. And I'm going to give you a little bit better version of it here in just a minute. Okay? And that, okay, let me see if I can explain this right. This what? Oh, I'm drawing a blank all of a sudden. Bad time for a blank. All right. Okay, since I'm blanking on that, let me just give you the definition. All right. The definition, two definitions. Write this down. Delta y equals f of x plus delta x minus f of x. Delta y means the change in y. Think of it this way. If we have a point x, f of x, and then we add a certain little amount to the x coordinate, that little amount we add is called delta x. The y, so if x has a y coordinate of f of x, x plus delta x would have a y coordinate of f of x plus delta x. Okay? Now, that is x1, y1. That is x2, y2. So, does this sort of make sense now? That's really just y2 minus y1. Wouldn't that give you the change in y? One of the y coordinates minus the other one? Yes? Okay? So it looks like a complicated definition, but, well, two things. One, it's a definition. We don't actually have to understand definitions as a student. Now, as a mathematician, yeah, okay? But I want you to. So, A, you don't have to understand the definition. I don't know why that's called a door. It just is, okay? But it makes more sense. I'm going to be able to remember it better if I can understand it. So if delta y stands for change in y, wouldn't it make sense that the y coordinate you end up with, the second point, minus the y coordinate you started with would be how much y changed? If y is 4 and it becomes 7, what's the change in y? 3. And how'd you get it? The second one minus the first one. Okay? So, all right. And then the other definition is this. dy is going to be an approximation. So delta y is approximately dy. And dy equals f prime of x dx. And one more weird, I kind of wish I hadn't even gone over anything. I should have just started here. So forget everything else I said before. If we just start here, I think we're okay. All right? And one other thing I need to tell you. Delta y and dy are not the exact same thing. They're approximately the same thing. Delta x and dx are the exact same thing. Because, you know, mathematicians made this up. Why would they be consistent? Math is great about using the same word or the same notation in two different ways. My geometry students are having a hard time with vertical. Vertical lines, vertical angles. I've got a few that think vertical angles are when one angle is above another angle, because that way they're up and down. And I couldn't figure out why they thought that. They're getting vertical line and vertical angles confused. So why would we use the same word for both things? Because we're math and we like to do that. We have a limited vocabulary. Don't make us learn different words for completely different ideas. That's just silly. All right. Let's see. Yeah, I just want to avoid that. All right. Now, dy is called the differential of y. Delta y is called the change in y. Delta x is called the change in x. Dx is also called the change in x. Dy is called the differential of y. And I'll come back to that. Let's do an example. Turn over to page 240. In exercises 1 through 6, find the equation of the tangent line t to the graph of f at the given point. Use this linear approximation to complete the table. Number 2, our function is f of x equals 6 over x squared. Our point of tangency is 2 3/2. And we're going to complete the table. First step is to find the tangent line. Okay? And what do we need to do to find the tangent line? Take the derivative. If f of x equals 6 over x squared, what's f prime of x equal? Yeah, here's what I'm doing. I've got 6x to the negative 2, right? So power rule it, get negative 12x to the negative 3, which I can write as negative 12 over x cubed. All right, so there's the derivative. That's a formula to find the slope of the tangent line. Let's find the slope of the tangent line at this particular point. At the point 2, 3/2, f prime of x will equal negative 12 over 2 cubed, which is 8. And negative 12 over 8 reduces to negative 3/2. That's the slope of the tangent line at that point. We can now find the equation of the tangent line at that point by using our point slope form. Y minus y1 equals m times x minus x1. So y minus, and then the y coordinate of our point of tangency is 3/2 equals m. Well, we just found that to be negative 3/2 at this point of tangency times the quantity x minus, and then we're given that the x coordinate of the point of tangency is 2. Then solve that for y. So I made that seem all complicated a while ago, didn't I? But it's not complicated. I messed up. So we've done that. All right, now, like we talked about, near the point of tangency, the tangent line and the function are going to have y values that are very close to each other. Okay? So, near the point of tangency. Well, and near and close, you know, those are terms that just vary from function to function, what's close enough. If the point of tangency is 2, they've decided that 1.9 and 2.1 are as far away as they want us to go. Okay? So let's make our table. T of x is the notation they're using for the tangent line. All right, let's get our calculators out. And we can actually do all this at once here. Let's make y1 our function. And let's make y2 our tangent line. Let's make sure that our table is set for the independent variable to ask. Everybody caught up with me? So y1 is the function, y2 is the tangent line. Set your table to ask for the independent variable, and we should be able to knock this table out in just a few keystrokes. So then we go to table, and we get rid of all the stuff that's already on there. All right, we need 1.9. So when x equals 1.9, our function has a value of 0.662. Our tangent line has a value of 1.65. So within 100th of each other. Pretty close. When x equals 1.99, now they're within a 10,000th of each other. That's really close. x equals 2. They're equal. They better be, because that's the point of tangency. 2.01 and 2.1. So like I said, this is a bit of a history lesson more than a actual need to be able to work this kind of problem, because what am I doing to do the tangent line and the function? A calculator. Couldn't I have just done it on the calculator without using the tangent line? Yeah. Okay. But can you see how 50 years ago this would have been a real time saver? Maybe not with 6 over x squared. And probably crunch that out. But you get the idea? Guess what kind of calculator I used when I took calculus in 1981? I didn't use a calculator. They did exist. I carried an abacus with me. They did exist, but they weren't allowed. And all they would do is add, subtract, multiply, and divide, unless you wanted to pay like $1 million to get one that would like take a square root. Number 9. Yeah, it was just a TI. They didn't know they were going to make more than one. In exercises 5 through 10, use the information to evaluate and compare delta y and dy. Because delta x equals dx, but not so with the y's. So we have two different definitions. We have a definition of delta y. We have a definition of dy. For number 9, y equals x to the 4th plus 1. They tell us that x equals negative 1. And they tell us, where am I getting this from? Oh, yeah, it's just written out in the question. For some reason, I didn't copy it. And they tell us that delta x, which is the same thing as dx, equals 0.01. So all that's given to us. What we have to know is we have to know these definitions. Delta y equals y2 minus y1, which is f of x plus delta x minus f of x. dy is defined to equal f prime of x dx. All right, let's find these one at a time, okay? So to find delta y, well, let's see. Watch this here. X is negative 1, so I'm going to put a negative 1 there, plus delta x, so plus 0.01, minus f of x, so that'll be a negative 1 there. So when I do that, I get that line. Do a tiny bit of arithmetic. Negative 1 plus 0.01 is negative 0.99, so make it f of that. And then evaluate that function. In fact, evaluate both of these functions. The function is x to the 4th plus 1. So f of negative 0.99 becomes negative 0.99 to the 4th plus 1. Minus f of negative 1. So minus parentheses. Now, what's f of negative 1? Well, It'll be negative 1 to the 4th plus 1. And here's where we run into trouble without a calculator. We can all figure out what negative 0.99 times negative 0.99 times negative 0.99 times negative 0.99 is. We can all do that, but it's going to take a while. So it's 0.9605961 plus 1 minus, well then what's in that last parentheses? 1 plus 1 is 2. So 0.9605961 plus 1 minus 2 equals negative 0.03940399. And I rounded that because on the AP test, all your answers are going to be rounded to 3 decimal places. So to the nearest thousandth. In fact, they would even take it if you rounded wrong, as long as you just stop at 3 decimal places. For instance, if that was a 6, so we ought to round up, but you still call it 0.039, they'll accept it. Okay? So either truncate it, which means cut it off at 3 decimal places, or round it at 3 decimal places. I prefer rounding because, duh, that's the way you're supposed to do it. But they take it either way. All right, so that took a little bit of work, right? Let's see how dy works out. dy equals f prime of x dx. What is f prime of x? 4x cubed. So dy equals 4x cubed dx. So dy equals 4 times, what they tell us x is? Negative 1. So 4 times negative 1 cubed times, what they tell us dx is? 0.01. So you'll get a negative, and then what's 4 times 0.01? Yeah, 0.04. Is negative 0.04 fairly close to negative 0.039? Yeah. Yeah. My explanation was horrible, but these problems aren't so bad. Yeah. Uh-huh. Here? All right, I'm taking whatever's inside the parentheses and substituting in for x. If all I was looking for was f of 2, it'd be 2 to the 4th plus 1. If it was f of 5, it'd be 5 to the 4th plus 1. It's f of that, so it's that to the 4th plus 1. All right, let's do another one. Okay, before we do that, I need to talk about this. Physicists and engineers tend to make liberal use of the approximation of delta y by dy. I'll have to take their word for it. I've never been a physicist nor an engineer. One way this occurs in practice is in the estimation of errors propagated by physical measuring devices. For example, let's talk about that for an example. Whenever you measure something with a ruler, aren't you always estimating just a little bit? I mean, it just never ends up right on a little mark, does it? And even if it does, the mark itself has some width to it. So which should it be? The middle of the mark to be exact? The left edge? The right edge? So there's always just a little bit of guesswork, okay? So whenever you measure something, and then let's even get things that are harder to measure than like a line. Like you're given a sphere, and you're supposed to measure its diameter. You'd get those, what are those things called? The little pinchy things, but they're not called the little pinchy things. Calipers?
Yes.
All right, and you measure those, and you get the diameter. You're always going to be just a little bit off, okay? Just because your measuring device is not perfect. So the difference between the actual, what, as far as I know, only God knows what the true diameter is, and what you measure it to be is called the propagated error. There's going to be error, okay? When you make things, there are always tolerances, okay? If you're making ball bearings for something, they all have to be within a certain tolerance. They're not all identical. They're made on the same machine by the same person running the machine, and not every one of them is identical because they're just not going to be. But they have to be within, let's say, 1,000th of a centimeter from each other, or whatever that tolerance is. So they know there's going to be some error. All right, now back to this. For example, if you let x represent the measured value of a variable, and let x plus delta x represent the exact value, okay? So x is what you measured, x plus delta x is what it really is. Now see, delta x could be positive or negative, because what it really is could be a little bit bigger than what you measured, or a little bit smaller than what you measured. And hopefully delta x is really small, right? I mean, we're hoping that we're not measuring a mark on the floor in inches and we're off by 100 inches. Okay, I mean, we really suck at measuring if we're off like that. So we're hoping that delta x is really, really small. All right, so let's see, where are we? Then delta x is the error in measurement. Finally, if the measured value x is used to compute another value, the difference between f of x plus delta x and f of x is the propagated error. All right, so let's go back to that sphere. We measure its diameter. We get 5. It's really 5.1. Then we use that to compute its volume. So we're doing the volume. What is the volume of a sphere? 4/3 pi r cubed. Is that it? Is that all there is? So we're doing that, and we're putting a 5 in there. But if we'd known that it was really 5.1, we would have done it like that. Aren't the results going to be off a little bit? Okay, so that's actually the propagated error. Once you've taken your measurement and used it to do something. Now, if I then used that volume to do something else with it, don't I compound the error again? Okay, so we got to be careful with that. All right, now, dy, which is the same thing, which is not the same thing as delta y, is approximately f of x plus delta x minus f of x. How do I know it's approximately that? Follow the lines of definitions we had before. Okay? We have delta y is f of x, no, f of x plus delta x minus f of x. Delta y is approximately dy. So that means that dy is approximately f of x plus delta x minus f of x. Okay? Now, if I solve this for f of x plus delta x, so I would take this, and I would add f of x to both sides to get dy plus f of x is approximately f of x plus delta x. Then I just rewrite it. F of x plus delta x is approximately f of x plus dy. So that can be used to approximate function values. Since dy is approximately delta y, then we do a little algebra manipulation, and I'm going to show you how we use that. Okay? So what you need to know is that I copied from my paper. The rest was hopefully explaining a little bit. All right, number 22. It says use differentials and the graph of f to approximate f of 1.9 and f of 2.04. All right, first let's do f of 1.9. We just figured out that f of x plus delta x is approximately f of x plus dy. Right? That's what we figured out here. Now, they want us to find f of 1.9, or actually to approximate f of 1.9. X is 2, because that's the point I know. Okay, 1.9 is close to 2, and that's the point of tangency that we're working with. Okay? And delta x then, all right, if x is actually 2, but we're going to use 1.9, isn't there a 0.1 difference? Okay? Now, how come I chose negative 0.1? Yeah, real minus approximate. Okay? No, I did it the other way around, didn't I? Approximate minus real. We're starting with 1.9 because that's what they want us to use, minus the other one. And it's kind of a plug and chug from there. F of x, if x is 2, is f of 2. F prime of x, if x is 2, is f prime of 2. Dx is negative 0.1. How do I know that f of 2 is 1? Yeah, because it says so right there. Okay? How do I know that f prime of 2 is negative 1? It's the slope of the tangent line by inspecting the graph. And then you do the arithmetic. Negative 1 times negative 0.1 is 0.1. 1 plus 0.1 is 1.1. So, never underestimate the ingenuity of people that write textbooks and make questions. They figured out a way to force us to use approximations instead of a calculator by simply not telling us what the function is. Okay? To approximate, that is, f of 2.04. X is still 2. Delta x, all right, it's what they told us to use minus the x value. That's how we're getting that. What they told us to use minus the x value. 31. The measurement of a side of a square is found to be 15 centimeters with a possible error of 0.05 centimeters. A, approximate the percent error in computing the area of the square, and then we'll look at B in a minute. Percent error. All right. I need to know the error before I can get a percent error. So let's simplify it. Let's find the error in computing the area. Okay? So instead of a Y, I'm going to use A for area. But it's the same idea. Okay? Now let's let X equal the length of a side, and they tell us that we measured it to be 15. So I'm going to say X equals 15. Why did I choose X? Well, just because we're used to working with X's, functions of X, that's generally what we do. Okay? Now, when they tell us that the possible error is 0.05, what are they telling us? Are they telling us delta Y, dy, delta X, or dx? They're telling us delta X and dx. Use whichever notation you want. Okay? Delta X is what we've been using, so delta X. And I know that if it's a square, that its area is X squared. Now, we have this. We know that dy is approximately f prime of x dx. But I'm going to use a instead for area. So dA, I should have written, is approximately f prime of x dx. What's our f of x? I never wrote f of x anywhere. Yeah, it's the x squared. It's a because I wrote a instead of y, right? So that's our f of x. So if dA is approximately f prime of x dx, what is f prime of x? 2x dx. What am I going to substitute in for x? 15. What am I going to substitute in for dx? And now what am I going to do? Simplify. So that's how we find the approximate error in computing the area. Okay? So that's the propagated error in finding the area. But they want us to find the approximate percent error. All right? And it's actually fairly simple. Percent error is just the error divided by what you thought the amount was. Okay? So percent error is the amount of error divided by what you think the amount is, what you measured it to be. In symbols, for this problem, what symbol represents the amount of error in computing the area? dA. What symbol represents the measured area? A. What is dA? We haven't found this yet. What's A? 15 squared. I didn't need it until now. So, but the measured area is 15 squared. So that's 1.5 over 225, which I then convert into a percent. So just divide it, you get 0.006666666666666666. Change that to a percent, which means move the decimal 2 places to the right. 0.66666666666% or 2/3 of a percent. Part B, estimate the maximum allowable percent error in measuring the side if the error in computing the area cannot exceed 2.5%. So the percent error must be less than or equal to 2.5%. That gets me that. Okay. Now, I'm not even worrying about the question yet. I'm going to convert that into my symbols. What was my percent error? It was dA over A. So replace percent error in the words with the symbols dA over A. And then percents are just boogers to work with. So change the percent to a decimal, less than or equal to 0.025. All right. Now, it says estimate the maximum allowable percent error. Okay. Let's see. It's a different percent error they were asking us for. They're not asking us for D over A. They're asking us for the percent error in measuring the side. All right? We haven't talked about that in this problem yet, but think about it. If, how can I say this? If dx is our error in measuring the side, then that's how we got 2x dx, dA equals f prime of x dx, to be the amount of error in measuring the area. Okay? So I can replace dA with 2x dx. So I'm going from there to there. And then A is x squared. Now, you see I wrote over here to find dx over x. Well, isn't that the percent? If this is our percent error, wouldn't that be it? The amount of error in measuring x is dx over the measured amount, x. So I'm not solving it for x. I'm solving it for dx over x, which is strange. Okay? All right, so the first thing I can do, divide that into that, get 2 dx over x. Ooh, practically there. Multiply by a half, and now I have dx over x. Then I change it to a percent.